Greetings, folks. So this is the impulse lab. The whole idea behind the impulse relationship is the idea that the force that's applied over a time interval on an object is going to end up changing its momentum. And so the left-hand side of the impulse equation is F delta t, which, if you think about it, is the area under a force versus time graph. And according to the relationship, whatever that area is going to end up equaling the change in the momentum of the body. And so that's what we're going to be looking at in this lab. The setup, we have a force transducer here, which will end up measuring force, obviously. We've got a glider. So the glider is going to come in. It's going to strike the force transducer. It's going to bounce off. And in fact, this force transducer takes like 10,000 data points a second. And so we're actually going to end up getting a graph of the force as a function of time in real time, or at least a pretty good approximation. Actually, I only have it taking about 500 data points a second, so the graph isn't going to be a perfect smooth curve. It's going to be a little jaggedy, but it's the best we can do. In any case, it's going to come down, it's going to hit, it's going to bounce off. Force transducer is going to dump its information into a computer via LoggerPro. Additionally, over here, I have a motion detector, which is basically using it's a sonic device that is checking to see where this body is as a function of time. And knowing where it is as a function of time, it can actually come up with a velocity versus time graph. And so we will have all of the ingredients that we need, given that we know what the mass of this card is, and I've measured that, and I will tell you what that is here shortly. To figure out what F delta t is, that will be the area under this force versus time graph, and what delta p is, which is the change in the momentum. Okay, so we're going to give this thing a try and see what happens. So I'm going to go ahead and start her off. I'm going to bring the camera in closer so you can see what's on the computer screen, and we'll take the data. Okay, so if we look at this fairly closely, you will see that here is where the impulse occurred. This is where the force transducer was struck. This is happening right around 1 second. So if we come over here to approximately 1 second, you will see that the velocity is in one direction, then it transits. So I went ahead and tried to magnify the area, and this is what I got. You can see that you have the force increases with time until some maximum, and then it dies out, which is what you'd expect. You will notice that there is a kind of an artifact here, which is sort of unfortunate. I suspect it has something to do with the force transducer actually vibrating during the course of the collision. This kind of thing happens, and there's not a whole lot we can do about it. If I want the area under that curve, I can go ahead and highlight the region that I'm interested in, and then go up to the integration tool, and the computer will actually calculate what that area is. And according to the calculation, it's 0.5002 Newton seconds. When I expanded the size of the velocity graph, this is the incoming velocity here. And if I go ahead and put my cursor here just to see what that incoming velocity is, it's reading down here 0.503. And if I put the cursor down here, I come out with V coming out as minus 0.429. So that is our data. And I've written it all out here for you so you can see it in living color. In theory, if you've got F delta t, that's the area under the curve. You know the mass, you know the incoming and the outcoming velocities, so you should be able to figure out what the change of momentum is pretty easily. Hopefully those two numbers are effectively going to be the same, because that's what the impulse relationship suggests should be the case. So we'll see. Anyway, that's it.
a nice day.